clickers, and then we're going to get on to water. Really important. Who would like to tell me your answers to this one? Anybody would like to volunteer your answer to this clicker? Sophie?
I said all of them.
Yeah, I did too. Any questions?
Can we go over C?
C. At the end of the proximal tubule, the concentration of glucose in tubular fluid is lower than in the plasma of peritubular capillaries. That's true because we have pumped glucose from the lumen into the interstitial space where it is picked up by capillaries. So we have used active transport to zero out the concentration of glucose in the tubular fluid at the end of the proximal tubule is 0. So that it has to be lower than in the plasma because the concentration of glucose in plasma is not 0. It's higher than 0. Okay, so that's why that's true. Other questions? All right, let's do the next one. Anybody want to tell me your choices for this clicker? Richard?
I said B and D.
B and D, that's what I said too. Any questions? All right, let's do the next one. So the top one, what did people say? Somebody suggest an answer. I'm trying to get a conversation as necessary. Yeah.
I had A and B.
A and D?
Yeah.
Which of the following is important for all segments of the renal solute? Paracellular is important only in the proximal tubule. So you were half right. A is the only true statement. Sodium, potassium, ATPase is expressed everywhere. This is expressed only in the proximal tubule. This is expressed only in the ascending limb of the loop of Henle. This is important primarily in the proximal tubule. Not certainly, and this is not true in the ascending limb of the loop of Henle. Okay? Why did humans evolve the ability to secrete and reabsorb potassium? Somebody tell me an answer to this one. CJ? C. That's what I got too. C. Sodium is a rare commodity in the diet that we evolved with. Very good. Okay, mannitol. It's a sugar, but we don't metabolize it. It's an osmotic diuretic. This means it increases urine production via an osmotic mechanism. We're going to talk more about water in a minute, so this is getting a little bit ahead of ourselves, but let's see how you did. Mannitol is freely filtered at the glomerulus but is not reabsorbed. Which of the following is true? What did you get for this?
I put A, C, and D.
A, C, and D. I said they were all true. So let's go. So you had A, C, and D. B is also true, and we'll talk about that more in the next hour. Questions about A? So let's leave B aside because we'll talk more about that. Any questions about A, C, and D? Yes.
For A, are you just assuming that the secretion doesn't need, like, it does need to be mentioned that it's not? Or, because I think I got confused because I was thinking, like, it needs to mention something about secretion in order to be.
So A is true because it anything that is freely filtered and not reabsorbed, that's the definition of something that could be used to measure GFR. So this right here is the definition. That's the same for creatinine, it's the same for inulin, and it happens to be true for mannitol. So that's why A is true. Does that answer your question?
Yes. Yeah, I think I can answer my question by looking back at other slides.
Okay. I'm happy to follow up if you can articulate a question.
Well, I think, does anything like with like these type of things that they are used to measure GFR, can it mention something about like being secreted or not secreted? Like, can you add in there that it will also result in measuring GFR? Or are you just going, like, are you just looking for like, if it's freely filtered and not reabsorbed?
If it's freely filtered and not reabsorbed, it would be a way to measure GFR. If it were freely filtered and its reabsorption and secretion were exactly opposite, so that so that they balanced each other out, so that every bit that was reabsorbed was secreted, and I think this was a question on your quiz, then it would also that would be the same as if it were not reabsorbed at all. So if secretion and reabsorption are exactly opposite in both, they're always opposite in direction, and if they're opposite in magnitude, if they're equal in magnitude, then then mannitol would also be something that could be used to measure GFR. Did that answer your question? Yeah, this is getting to the question on the quiz. There was one of the trick questions I think it was the last question on the quiz. A was a correct answer because of this thing that we just talked about. Okay. Let's do this one, but we're getting into diuresis, which is what we're going to be focusing on in the next class, but let's just see how you did with understanding diuresis. Most diuretic drugs that increase the production of urine are used to increase the excretion of sodium excretion. Which of the following is true? Somebody volunteer an answer. Let me just see how you did before I teach it. A, B as in Bob, and C as in cat. That's what I got too. Questions? Okay. Oh, and there's another one. I thought we were moving on to water. Okay, we're talking about sodium diuresis. Sodium diuresis, sodium in the urine, sodium excretion. Yeah.
I had all of them.
Yeah, I did too. All of them would lead to sodium diuresis, but A would be a very bad drug because it would lead to glucose excretion, which we don't want to do. Okay, so good. So you've got a handle on diuretics. You've got a handle on excretion and secretion. I think you are ready to wrestle with water. And it will be a wrestle. So I'm not gonna try to do this whole part 3, but I do want to try to set this up so that we can move, so that on Wednesday we're well positioned to finish up. We're going to learn about water reabsorption, right? 99% of the filtered water is reabsorbed. If we didn't, we would urinate our life away in a few minutes. And it's going to be the loop of Henle, the vasa recta, and the collecting tubule that are the key players here. We need to learn how we reabsorb water and how we control that, because we have to reabsorb water at just the right amount. We don't want to become too concentrated. We don't want to become too dilute. Both of those lead to health problems. I can tell you a story about my mother-in-law who was having quite a lot of health problems, and she basically she became demented one day. She just lost her mind. And it seemed like she had a stroke. And she was so disoriented and demented. I mean, she just was doing the craziest things. And she didn't have a stroke. What she had was too much water. And so they gave her a diuretic, and she peed away a liter of dilute urine, and she came back. It was incredible. For someone to go from just crazy to normal because of urine. So it tells you how important this is. So here, let's just talk about homeostasis for a minute. You take in about 2.5 liters of water every day. This is obviously plus or minus. You drink about 1.2 liters of water and other drinks. You get about 1 liter of water from your food because it's got water in it, moisture. And you actually your body makes 300 mils of water a day. What part of your body makes water? Where do you make water? Self-is question.
Breathing?
What?
Cellular respiration.
Cellular respiration. Remember, oxygen, the final electron acceptor in cellular respiration, oxygen is reduced to water. Well, so you make water. You have to drink water because you can't make enough. But there are animals that live in the desert that actually make such a concentrated urine that they excrete almost no water. And they get almost all of their water from dry food by doing cellular respiration of dry food and making water from cellular respiration. It's incredible, these desert rats that do this. Anyway, you do it somewhat, but you don't do it enough you have to drink water. And so water input, water output, we're in balance. You urinate about 1.5 liters a day. That's 1 mil per minute is 1,400 mils per day, something like that. You excrete water in your feces, you sweat water from your skin, and you breathe out moisture from your exhalator. So this is how you get rid of water, and this is how you increase water, and so they're in balance. And this is just a slide I like to show that shows the variation from person to person. This is data taken from A&P students quite a few years ago. So what are we plotting here? This is osmolarity. What is the definition of osmolarity? Anybody know? It's basically the concentration of all solutes. So sodium chloride, potassium chloride, glucose, hopefully no glucose in urine, urea. It's the concentration of solute in urine as a function of time after a drink. So look at the variation from person to person. Here is a person that's making urine that's almost 1.2 molar, right? And here's a person making urine that's about 300 millimolar. Millimolar in solute. What's the difference between this person and this person? One of these persons is dehydrated, and the other person is fully hydrated. Which is which? Dehydrated. this person is making a concentrated urine because this person has not had a drink of water in a couple of hours. This person has been drinking water all morning and came to lab fully hydrated. And in between. So I noticed somebody's carrying around a gallon of water. Somebody is working very hard to maintain hydration. Your urine is down here somewhere, right? Like, is this intentional? You're trying to hydrate? Okay. And so I haven't had a drink of water since a cup of coffee at lunch. I'm up here by now. Then everybody had a drink of water. They had 500 ml, half a liter of water. And you can see within an hour, everybody was producing a dilute urine. And then it started to come back with some variation. Here was a different group of students who were told to not drink anything. Again, variation. A dehydrated person, a fully hydrated person, but the fully hydrated person, within an hour of not drinking, started to become pretty dehydrated. The dehydrated person stayed dehydrated, didn't increase. That was a little unusual, but maybe they snuck off and had a drink of water. I don't know. Compliance in this lab might have been so-so.
No, not drinking water for a good year. Every half hour.
If you try hard enough, you can pee off a little bit of urine every 30 minutes, even if you're dehydrated. If your professor says, go get a urine sample, you can get one. It can take some time to sort of relax enough to produce a urine sample, but you can do it every 30 minutes. It's just a little bit, but that's all we needed to make this measurement. Okay, so we're going to talk about this now. Water homeostasis. Let's get the big picture. The idea here is that the kidney makes a hypertonic interstitium in the medulla. That's key. The loop of Henle is going to build a solute gradient in the interstitium in the medulla. I'll explain how in a minute. But that's key. Then we are going to use variable water permeability in the collecting tubule and use osmosis to draw water, pull water from the tubular fluid into this hypertonic interstitium where it can then get recovered into the blood. And we control that water permeability in the collecting tubule. Why is this so complicated? Because sometimes we want to excrete a dilute urine. We not just want, need. Sometimes we need to excrete a dilute urine. And sometimes we need to excrete a concentrated urine. And so we have this system for making a concentrated urine, but then only using it when we need to. That's where we're going to go. The key thing to know where we're going is building a solute gradient in the interstitium of the medulla, using osmosis to pull water out of urine into the interstitium, and then deciding whether we want to use that mechanism or not. Okay? We need to talk about where urine is hypertonic, isotonic, and hypotonic before we get into this. So what do I mean by tonic? If something is isotonic, it means it has the same solute concentration as plasma. So filtrate is isotonic because it basically is plasma. Does that make sense? Filtrate is just plasma that's gotten out of the plasma and into the Bowman space. So since filtrate essentially is plasma, it's isotonic. Now, in the proximal tubule, why does it stay isotonic? We reabsorb sodium, active. We reabsorb water in exactly the same proportion. So by reabsorbing sodium and glucose and water in exactly the same proportion, the fluid stays isotonic. For every molecule of sodium, we reabsorb a molecule of water. And so the concentration of solute in the fluid stays the same. And it stays isotonic. We're going to see that it's going to become, that the tubular fluid is going to become hypotonic. Remember, hypo means low, so hypotonic means dilute. It's going to become dilute at the end of the loop of Henle. You're going to see how we do this, but it's going to become dilute. Then it either stays dilute or becomes hypertonic, becomes concentrated in the collecting tubule, depending on what we need to do. And we're going to get into the control of that by the end of the day on Wednesday. So this is the overview. This is what we need to do. And now I'm going to show you how our kidneys do this. Questions about the overview before I get into the molecular mechanisms? So let's just review with an image rather than words. You know I like to teach from pictures. Isotonic. Isotonic, because sodium and glucose and water are reabsorbed in proportion, in parallel. Isotonic. The fluid is going to become hypotonic by the time it gets here. The tubular fluid is going to become hypotonic, dilute. The interstitium is going to become hypertonic. And we're going to establish a gradient. It's going to become more hypertonic as we move deeper and deeper into the medulla. I'm going to show you how in a minute, but I'm just setting up what we're doing. Isotonic, hypotonic, stays hypotonic in the distal tubule. And then in the collecting tubule, as this hypotonic fluid moves through a hypertonic interstitium, if there is water permeability, water will be reabsorbed. And if there is no water permeability, water is going to be excreted. So the final step of whether we make a concentrated urine or a dilute urine happens right here. Okay, that's how we're going to go. So here's a slide from your textbook. Where are we here? So the proximal tubule has happened. What is 300? Why is 300 here? 300 is approximately the osmolarity of plasma. So 300 is isotonic. It's actually 290, but your book rounds it up to one significant digit throughout almost all of it. So this is isotonic fluid entering the loop of Henle. We're going to talk about we're going to talk in a minute about the transport mechanisms in the loop of Henle that build a solute gradient. So look what happens here. This is the concentration of solute in the interstitium. Remember that interstitium is not a big space here. It's a tiny little space, but it's there. Isotonic, hypertonic, really hypertonic. This is the solute gradient that the loop of Henle is going to build. We're going to talk about the mechanism in a minute. The loop of Henle is going to build this solute gradient. And it does it in a series of steps in the descending and the ascending loop of Henle. The distal tubule is hypotonic. And by the time we get, and then we have the collecting tubule, and if there is water permeability in the collecting tubule, then water is absorbed, and the fluid that is urinated, by now it's urine, is highly concentrated. This is the situation in a dilute, in a dehydrated scenario. We want to produce a concentrated urine. We want to conserve water. Key points: the loop of Henle builds this gradient, and the collecting tubule uses this gradient to suck water out of the urine so that the water is not excreted. Here's a situation. Oh, well, that's what I just said. So this is the same picture. The loop creates the osmotic gradient, and the collecting tubule uses it if necessary. But notice what happens. If the collecting tubule does not have water permeability, then what we do is we urinate something that is dilute. And that's what we do when we're highly hydrated. Okay, so now I've told you where we're going. What do I mean by that? I mean, we're going from isotonic fluid to hypertonic fluid using a solute gradient that the loop of Henle built and water permeability of the collecting tube. Okay? So let's talk now about how this loop-de-loop thing builds a solute gradient. We got to understand that. And here is the slide that explains it. Believe it or not. So let's walk through this. It's going to do it in a series of steps. Okay, so I'm just going to break it down into some steps. So here's the descending limb of the loop of Henle, here's the ascending limb of the loop of Henle, proximal tubule, distal tubule, right? So schematic. Remember, this is an epithelium, so this one line here is really two membranes. It's the apical and the basolateral membrane. Let's just start with everything being isotonic. This never happens. Never, ever happens. But in order to explain the story, we're going to start it with something simple, with everything being isotonic. Okay? We are never here. but let's just use that as a starting point. Remember, on the ascending limb, we had the sodium-potassium 2-chloride co-transporter on the apical membrane, and we had the sodium-potassium ATPase on the basolateral membrane. So we are pumping solute from lumen into interstitium in the ascending limb. Remember, there was essentially no water permeability. And I didn't say this, but the descending limb is really only passive. So we just have passive water flow. We don't have solute active transport. So passive transport, active transport, water permeability, no water permeability. That's key to understanding this. So we've started with everything being the same. Now let's turn on these pumps. Let's just activate them. They're always running anyway, but now we're going to see what they do. They pump solute from urine, from urinary fluid, into the interstitium. And they can maintain a certain differential. So we're going to say they can maintain 200 milliosmoles of differential across this epithelium. Right? And this epithelium and this epithelium are the same epithelium, right? We're just showing it going in this direction. But solute is getting pumped out of the fluid into the interstitium. And because the interstitial space is limited, it's getting concentrated, and the urinary fluid is getting diluted by that active solute transport. Okay, so does everybody believe that, given what I've just described, we could move solute from here to here? Now we also have to explain, so why did, when we move solute from here to here, when we turn 300 into 400, why did this become 400?
Does the solute, can the solute be reabsorbed?
If we think about solute, we're going to get confused. But if we just remember that this is passive and that this is going to equilibrate with this, then whatever we create here is going to happen here. So solute and water are going to move to equilibrate across this passive epithelium. So we have an active epithelium with no water transport, and we have a passive epithelium with water transport. Okay? So we pumped solute from the ascending limb into the interstitium, and we have equilibrated across the descending limb. So that's what we mean by pump equilibration. Pumping and then equilibrating. Does everybody believe that I could create something that looks like that, given the geometry and the pump and equilibration? Okay? I still don't have a gradient, but I'm going to get there pretty soon. So now we introduce a little bit of fluid here. Remember, there's fluid flowing from the proximal tubule. So some new fluid is going to enter here. So here's some new fluid. Here's the old fluid moving through this tubule. Right? So now, since this equilibrates, this equilibrates. Here's this is still equilibrated. This is still equilibrated. So this is just moving new fluid, shifting, and equilibrating. Okay? Now let's do this step again, because it's happening all the time. All of this, I'm breaking it down into steps, but this movement of fluid and this pumping and equilibration are all happening all the time. Okay, so now we pump, and we establish 200 milliosmoles of differential. We equilibrate. So already, just in these 1, 2, 3 steps, we've already seen. So we have established a gradient and a hypotonic fluid. And we're not done yet, but I've already, if you believe what I've said, when I said, do you believe that I can do this? Do you believe that I can do this? You've said, yes, 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 I believe that you can do this. And now you must, or I force you to believe that we have established a gradient in the interstitial solute, and we have made an hypotonic urinary fluid. we do this again. So bring in some new fluid, move the old fluid around, equilibrate across this membrane, across this epithelium, more of the gradient. Do that again, more pumping and equilibrating, more shifting and equilibrating, and we get to our final destination, which is a gradient and a hypotonic exiting fluid. That's the story of how the loop of Henle builds a solute gradient in the interstitial spaces surrounding it. Yes?
So what stops that number at like 1,200, like you had it on the graph, or is it?
Why does it not get higher than 1200? It's a limitation to the expression of the pump and the sodium-potassium 2-chloride cotransporter, and the fact that when I say there's no water permeability, I mean there's a tiny bit of water permeability, so that we humans can only make it up to about 1200. What would be your prediction for the desert rats? Those desert rats can build a sodium gradient, solute gradient that is about 4 molar, 3,500 instead of 1,200. How can they do that? They can do it by more expression, less water leakage, and a very long loop. So we are limited by the length of our loop, the juxtamedullary loop, the loops that go all the way into the medulla. We're limited by the length of the loops, by the expression of the pumps, and by the residual water leaks. Desert rats, I mean, it's incredible. They have these incredibly long loops. They have high expression of the pumps, and they have almost no water permeability, and they can make a solute concentration. They start here, like we do. They're mammals. Their blood is isotonic with ours, more or less. But the deeper medulla, the deep medulla of a desert rat is 3.5 molar. What's your prediction of a water rat? Does a water rat need to produce a very concentrated urine? So what do you think is different between a desert rat and a water rat? There are 3 things.
Shorter loop.
Shorter loops is one. Shorter loops. Less expression of the transporters. And more water permeability. So, using this mechanism of pumping no water permeability, equilibrating with high water permeability, and the shifting, the slow movement, slow shifting of fluid through this loop builds this gradient. If we didn't have this loop, it wouldn't build. If we didn't have solute transport, it wouldn't build. If we didn't have low water permeability here and high water permeability here, it wouldn't build. It's all a function of that, of having evolved this exact system. Incredible. Okay, so our loop of Henle, where's the energy? So you can imagine this must take energy. Where's the energy coming from? Building this gradient has to take energy. Where is it coming from? Where does all of our energy come from?
Glucose.
Okay, glucose, but what I'm thinking, what do we turn glucose into before it gets here? ATP. And what protein is using ATP to make this gradient? The pump, the sodium-potassium pump. So we burn a lot of ATP to make this gradient. Now we have to talk about how we get this. Well, so now let's talk about the vasorectum. remember the loop of Henle has just just used a lot of ATP to make the solute gradient, going from 300 milliosmolars to 1200 milliosmoles as we move down into deep medulla. Now we have to understand the vasorecta. And the key thing, why did we evolve this loop of blood that parallels the loop of urinary fluid? The simple reason is that the vasorecta follows the loop of Henle so that it can absorb solute, because we need to reabsorb some solute, without washing out the gradient too much. So imagine what would happen if we just had blood flow moving across here. Let's just imagine, let's go back to a slide that's semi-realistic. If we just had peritubular capillaries moving through here, instead of the loopy vasorecta capillaries. If we just had peritubular capillaries working here, what would happen? We would build this gradient, and then if blood flow is 300 milliosmoles going through this way, 300 milliosmoles going this way, 300 milliosmoles going this way, it's going to wash out this gradient, big time. We're going to have 300 milliosmoles blood in contact with 1200 milliosmoles interstitium, and the blood is going to pick up all that solute that we worked so hard to build. But by having the vasorecta parallel it, we only lose a small amount of solute in the, we pick up some of the solute that we need to pick up, but we preserve the interstitial gradient better than if the blood had simply percolated across. Right? So the vasorecta preserves the gradient that the loop of Henle builds. What are all these arrows? You don't have to follow. If you try to follow each arrow, it's kind of pointless. The point is, we have built this gradient, and the vasorecta keeps the gradient, more or less. So now I want to go back to the beginning slide. Remember, we built this gradient. Now it's the collecting tubule that decides whether to use the gradient and make a concentrated urine or not. And how does it do that? It does that by controlling the water permeability. So this is a slide that shows different nephron segments. So here's proximal tubule, here's descending limb, here's ascending limb. All of this is, we can just call this all ascending limb. Distal tubule, collecting tubule. So simplify this by just saying proximal tubule. Did I give you this one or did I not? Proximal tubule, descending loop of Henle. All of this is ascending loop of Henle. Distal tubule, just use both of these as distal tubule. And collecting tubule. So notice that the proximal tubule has high water permeability at all times. I've told you that. It has paracellular water permeability. It reabsorbs water as it reabsorbs solute. It has high water permeability at all times. The descending loop of Henle has high water permeability at all times because that's how we do that equilibration in the descending limb of the loop of Henle. The asynchronous glucophenolate has low water permeability at all times, because that's how we build the interstitial gradient. The distal tubule has low water permeability at all times, because that's how we keep the distal tubule hypotonic. And now you can see, in the presence of a hormone called vasopressin, AVP stands for arginine vasopressin, because we have two forms of vasopressin. This is vasopressin. It's a hormone from your pituitary gland. Vasopressin controls the permeability of the collecting tube. So if the permeability is high, we reabsorb water in the collecting tubule, and we produce a concentrated urine. In the absence of vasopressin, we produce water permeability is low, and we produce a dilute urine. It's vasopressin that controls the water permeability of the collecting tubule. So let's do this and then we'll be done for today. So just two more slides. And stay with me here, because this is the summary of this whole thing that I've been teaching for the past 45 minutes. So what's this? This is the loop of Henle. Proximal tubule is cut off. Here's the distal tubule. Here's the collecting tubule. Here's the vasa recta. Bad cartoon because it suggests that there's lots of space here, but it's all packed together. This is a dilute urine. This is a person like Mike who's drinking a lot of water. And I see water bottles all over the place. A lot of you are in this position. I don't mean to pick on Mike. You're fully hydrated. Your pituitary has said, I'm fully hydrated. I do not need to release vasopressin. Low vasopressin. Isotonic builds solute transport, building a gradient from 300 to 500, but it's not being built maximally because you're fully hydrated. So we don't need the 1200 here because we're not dehydrated. How did we control, okay, let me jump. How did we control going from 1200 to 500 here? Aldosterone, another hormone. Remember renin, angiotensin, aldosterone. Aldosterone low aldosterone, low expression of these pumps. Low expression of pumps, low building of the gradient. Right? So if we have fewer of these pumps, we don't build the gradient. We stop here instead of building it all the way up to here. So, aldosterone says we don't need to build the gradient. We don't need to build it fully. We need to build it some, but not fully. So we lower the expression of the transport proteins, both the sodium potassium ATPase and the sodium potassium 2-chloride co-transport. The transport proteins that did this. Hypotonic in the distal tubule, hypotonic in the collecting tubule, hypotonic in the urine, because we don't have vasopressin, so we don't have water permeability here. Does that make sense? That's clear. Fully hydrated, low vasopressin, low aldosterone. Low aldosterone means the loop of Henle doesn't build the full gradient. Low vasopressin means the collecting tubule doesn't suck the water out of the urine, so the water gets excreted. Let's do the dehydrated state. This is me. I haven't drunk water in hours. Isotonic. High aldosterone. Lots of transport. Steep, full gradient. Lots of vasopressin. My hypothalamus is saying, you're dehydrated. Lots of vasopressin. Lots of water permeability, sucking the water out of the urine so that we're making a concentrated urine. The difference is high aldosterone builds more of a gradient, and high vasopressin uses the gradient more to suck water out of the urinary fluid. Let's stop here. I'm going to start on Wednesday with you'll love this. We'll start on Wednesday with a G protein coupled receptor. The vasopressin receptor is a GPCR that is coupled to, I bet you could tell me what type of G protein this is, right? Got to be GS. We'll talk about the GPCR, the response to vasopressin, and how that makes water permeability. We'll start with this slide on Wednesday. What I want you to do is tell yourself this story, the story that is embedded in this slide. What does the loop of Henle do? What does the vasorecta do? What does the collecting tubule do when we are hydrated and when we are dehydrated?